Imagine moving away from the Sun until the familiar worlds of the solar system disappear behind you. Earth becomes impossible to recognize. Jupiter and Saturn retreat into the distance. Eventually, even Neptune, the last recognized planet, begins to shrink against the darkness. Ahead, there is no obvious destination. No bright world waits just beyond Neptune's orbit. No visible sign announces that one region has ended and another has begun. The farther you travel, the more natural it becomes to assume that the solar system is simply running out. But that assumption depends on an image of the solar system that was never complete. Most of us first encountered our cosmic neighborhood as a line of planets arranged around the Sun. Each world occupied its own place, and the final planet seemed to mark the outer limit. Beyond it, the diagram usually offered little more than empty space. The actual solar system does not follow that simple picture. Neptune circles the Sun at roughly 30 times the distance between Earth and the Sun. That is already far beyond the scale of everyday experience. Yet passing Neptune does not take you beyond the Sun's territory. It takes you into a region where familiar planetary landmarks disappear, while other kinds of structure begin to matter. Some of those structures contain icy bodies that formed during the early history of the solar system. Some are defined by streams of particles flowing outward from the Sun. Others can only be understood through the paths of distant objects that move under the Sun's gravity. These boundaries do not occupy the same place. Its outer regions do not end together because sunlight, particles, gravity, and orbiting bodies follow different boundaries. A spacecraft can move beyond the last recognized planet while remaining surrounded by objects that belong to the Sun's extended family. It can later cross into material associated with the space between stars while still traveling through a region where the Sun's gravitational influence has not disappeared. That distinction changes the question entirely. Asking what lies beyond the last planet is not the same as asking what lies beyond the solar system. One question begins at Neptune. The other depends on what we mean by the solar system in the first place. Do we mean the region occupied by planets? Do we mean the bubble formed by the Sun's outward flow of particles? Or do we mean the much larger territory, containing distant bodies still connected to the Sun through gravity? Each definition produces a different frontier, and each frontier is known in a different way. Some objects beyond Neptune have been detected with telescopes. A small number have been examined closely by spacecraft. 2 spacecraft have measured conditions at the outer boundary of the Sun's particle environment. Other distant regions have never been seen directly and are instead inferred from the movements of bodies that occasionally travel inward. That difference matters. A photographed object, a measurement collected by a spacecraft, and a region reconstructed from indirect evidence do not carry the same kind of certainty. Understanding what happens beyond Neptune requires keeping those categories separate, even when they describe parts of the same enormous system. The darkness ahead is therefore not a blank space waiting for imagination to fill it. It is a frontier built from different kinds of evidence, different physical processes, and different ideas about where a star's surroundings finally give way to the galaxy beyond. The journey begins with a simple image: Neptune behind us, the Sun far away, and no other recognized planet visible ahead. But before we can understand what lies beyond that final world, we need to settle a question that seems straightforward until we examine it closely. Why is Neptune considered the last planet at all? And what changed when another familiar world, once placed beyond it in nearly every classroom diagram, became part of a much larger story? For many people, the last planet was never Neptune. It was Pluto. That was the picture printed in textbooks, displayed on classroom walls, and repeated whenever children learned the order of the planets. Mercury came first. Neptune appeared near the end. And beyond Neptune, small and distant, Pluto completed the familiar arrangement. Then the arrangement changed. Pluto did not disappear. Its orbit did not suddenly shift, and its physical character did not become less interesting. What changed was our understanding of the neighborhood around it. For a long time, Pluto seemed unusual but separate. It was smaller than the major planets, followed a more stretched orbit, and moved along a path tilted compared with the familiar planetary pattern. Yet when it was treated as a solitary outlier, those differences could be absorbed into the broader idea of what a planet might be. The problem emerged when astronomers found that Pluto was not alone. Far beyond Neptune, observations began revealing other distant bodies moving around the Sun. These discoveries changed the context. Pluto no longer looked like a single exceptional planet sitting beyond an otherwise complete system. It increasingly appeared to belong to a broader population of objects sharing the outer reaches of the Sun's domain. That raised an unavoidable question. If Pluto counted as a planet, which of these other bodies should count as planets too? A useful scientific category needs boundaries that can be applied consistently. Without them, every new discovery creates uncertainty about whether it belongs inside the category or outside it. As the outer solar system became more populated, the familiar meaning of the word planet needed a clearer definition. In 2006, the International Astronomical Union adopted a formal set of criteria for planets in our solar system. The first condition is straightforward. A planet must orbit the Sun. Pluto satisfies that requirement. So does Neptune. Both travel around the same star, even though their paths occupy very different parts of the solar system. The second condition concerns shape. A planet must have enough mass for its gravity to pull it into a nearly round form. This does not mean a world has to be a perfect sphere. It means gravity has become strong enough to give the object an approximately rounded shape rather than leaving it as an irregular fragment. Pluto satisfies that condition as well. The third requirement is where the distinction appears. A planet must have cleared the neighborhood around its orbit. That phrase can sound misleading. It does not mean the surrounding region must contain absolutely nothing else. Planets can share their general surroundings with smaller objects. The important question is whether the planet has become the dominant body in its orbital region. A dominant planet shapes the movement of smaller nearby bodies through gravity. Its mass and influence separate it from the population around it. In that sense, clearing a neighborhood describes a long-term relationship between an object and the other material moving through the same part of the solar system. Neptune meets that requirement. Although distant objects exist beyond and around its orbital region, Neptune is a major planet whose gravitational influence helps organize the environment near its path. It is not simply one member of a large collection of similarly placed small bodies. Pluto occupies a different position. It is round, and it orbits the Sun, but it shares its region with many other objects. Rather than standing apart as the dominant gravitational presence, Pluto belongs to a broader population of distant bodies. Under the formal definition, Pluto meets the first two requirements, but not the third. That makes it a dwarf planet. The name can create the wrong impression if it sounds like a judgment about importance. Dwarf planet does not mean that Pluto is unworthy of attention or that it somehow failed as a world. It identifies a different category of object, one that shares important properties with planets, while occupying a different relationship to its surroundings. Pluto did not become less real when its classification changed. Its surface remained its surface. Its orbit remained its orbit. The change happened in the map we used to organize what we had discovered. That distinction matters because scientific classifications respond to evidence. When a familiar object appears alone, it may seem to fit one category. When observations reveal that it belongs to a larger family, the category may need to be reconsidered. The discovery was not simply that Pluto was smaller than expected or different from Neptune. The deeper discovery was that the outer solar system contained a population that the traditional diagram had not adequately represented. This is why Neptune now marks the outer limit of the recognized planets. It satisfies the formal criteria, including gravitational dominance in its orbital neighborhood. Pluto does not satisfy that final condition, even though it remains a rounded world orbiting the Sun. But calling Neptune the last planet answers only a narrow question. It tells us where the sequence of recognized planets ends. It does not tell us where the Sun's extended family ends, where distant orbiting bodies disappear, or where the surrounding structure of the solar system gives way to something else. A classification describes what kind of object we are discussing. It does not draw a physical wall through space. Beyond Neptune, Pluto remains present, along with other bodies whose existence transformed the way astronomers understood that region. The final planet is therefore not a marker of emptiness. It stands near the beginning of a wider population that does not fit the familiar planetary sequence. That is the real importance of Pluto's changed status. The old diagram seemed to lose a planet. The more accurate picture gained an entire category of distant worlds. The change replaced a familiar sequence with a more careful distinction between dominant planets and the smaller rounded worlds that share their increasingly distant orbital surroundings. To understand what lies beyond Neptune, the next question is no longer whether Pluto deserves its former label. The question is, what kind of region contains Pluto and the many other objects that changed our understanding of the outer solar system? Because once Pluto is recognized as part of a population, rather than an isolated exception, the darkness beyond the last planet begins to acquire structure. And that structure has a name. The name of that region is the Kuiper Belt. It begins beyond Neptune, where the familiar sequence of major planets gives way to a more scattered collection of smaller worlds. Pluto belongs to this population, but it is not the only member, and it does not define the region by itself. The Kuiper Belt changes the appearance of the outer solar system because it replaces the idea of a final isolated world with the reality of an extended community. To understand where that community lies, it helps to use a unit designed for distances within the solar system. An astronomical unit is approximately the distance between Earth and the Sun. Instead of repeatedly describing enormous distances in ordinary units, astronomers can compare locations with this familiar baseline. Earth orbits at about 1 astronomical unit. Neptune lies roughly 30 times farther from the Sun. The main region of the Kuiper Belt begins around that distance and extends outward to approximately 50 astronomical units. Those numbers describe a broad region, not a perfectly drawn border. Nature does not place a fence at either end. The belt is often described as a disk or a donut-shaped region. That description is useful because many of its objects move around the Sun in a broadly similar part of space, rather than arriving equally from every direction. But the word belt can also create the wrong impression. It might suggest a crowded ring of objects packed closely together, with pieces of ice passing beside one another in constant motion. A spacecraft traveling through such a place might seem as if it would need to weave around obstacles. The actual region is nothing like that. The distances between individual bodies are enormous. Even where many objects exist, they are spread across a volume so large that the space between them dominates the experience. A traveler passing through the Kuiper Belt would still see mostly darkness. The significance of the belt comes from the number of objects distributed across the region, not from the idea that those objects form a solid or crowded barrier. This distinction matters because abundance and density are not the same thing. A region can contain a vast population while remaining almost empty at any particular location. The wider the territory, the farther apart its individual members can be. That is the situation beyond Neptune. The objects moving through this region are often described as icy bodies. Here, ice refers to material that can remain frozen in the cold outer solar system, mixed with other matter left over from the system's early history. Some bodies are small and irregular. Others are large enough to become rounded under their own gravity. Pluto belongs among the larger and more familiar examples, but its importance lies partly in what it revealed about the company around it. The Kuiper Belt is not a collection of identical miniature planets. Its members vary in size, shape, and orbital behavior. What connects them is that they occupy the distant region beyond Neptune and preserve evidence of an outer environment that was poorly represented in the old planetary diagrams. There is also an important difference between the objects astronomers have observed and the number they estimate may exist. An observed object is one that has been detected and tracked. An estimated population is a scientific judgment about how many additional bodies may remain beyond the reach of current observations. Those two numbers should not be confused. Distant objects are difficult to detect because they are small, far away, and faint. A telescope does not automatically reveal everything that exists in the region it examines. What astronomers see depends on the brightness of an object, its position, and the portion of the sky being observed. The known objects therefore represent a sample, not a complete inventory. Scientists can use that sample to estimate a larger population, but such estimates depend on assumptions about what has been missed. The result is useful, yet it does not mean every predicted object has been photographed or individually counted. That difference between detection and inference helps explain how the Kuiper Belt became established as more than an attractive idea. Before large populations of distant objects were identified, scientists had considered the possibility that material remained beyond the recognized planets. Such predictions described what might exist, but a prediction alone could not confirm that a broad population was actually present. The evidence changed when astronomers began finding objects beyond Neptune that were not simply Pluto. In 1992, an object later named Albion was discovered in this distant region. Its importance did not come from being the largest or most dramatic world beyond Neptune. Its importance came from what its presence suggested. Pluto was not necessarily a lonely exception at the end of a planetary lineup. Other bodies occupied the same broad outer territory. As more objects were found, the idea of an extended belt gained a stronger observational foundation. One discovery did not provide a complete map, but it helped turn a proposed outer population into a region that telescopes could investigate directly. Each additional object added another point to that developing picture. The outer solar system became less like an empty margin beyond Neptune and more like a landscape whose contents had been difficult to detect. The discoveries changed the meaning of distance. Moving farther from the Sun did not remove an object from the solar system, but placed it within another part of its system. The emerging map also revealed that these objects do not all move in the same way. Some follow relatively stable paths through the main part of the belt. Others occupy orbits connected to Neptune through repeating patterns. Still others travel along paths that take them farther away. These differences matter because an orbit is more than a location. It records how an object moves, how close it comes to the Sun, and how its path relates to the larger bodies around it. When many objects display recognizable patterns, those patterns become clues about the structure of the region. The Kuiper Belt is therefore not simply a distant storage area filled with frozen leftovers. It is an organized, though uneven population, whose members share an environment while following distinct routes through it. For the question of what happens beyond the last planet, this offers the first clear answer. Beyond Neptune, the solar system continues through a broad region containing distant icy bodies, including Pluto and many other objects that never appeared in the familiar diagram of planets. The region is sparse rather than crowded. Its main population occupies a range of distances rather than a rigid boundary, and its known members represent only the portion that present observations have revealed. Yet understanding where these objects are does not explain why their paths differ. A simple untouched ring might be expected to look more uniform. Instead, the outer population contains patterns, groupings, and orbital relationships that suggest a more complicated history. Some objects appear to move in step with Neptune. Others follow routes that stretch beyond the main concentration. The region has structure that cannot be understood by counting bodies or measuring distance alone. Something shaped the arrangement. And if the objects beyond Neptune preserve evidence of that shaping, then their orbits may tell a story that reaches back to the early solar system itself. The belt is not merely what lies beyond the last planet. It may also be a record of how that planet helped create the frontier we see today. To understand why the outer frontier looks the way it does, it is not enough to ask where its objects are. We also have to ask how they move. Every distant body follows a path around the Sun. Some paths are relatively steady. Others stretch outward, tilt away from the broader arrangement, or repeat their relationship with Neptune over long periods. Those differences are not merely details on a map. They are clues. An orbit carries information about the forces that have acted on an object. Its shape can reveal whether the object has remained comparatively undisturbed or whether gravitational encounters altered its path. Its relationship with neighboring bodies can suggest whether their movements have influenced one another over time. The outer solar system is therefore more than a collection of distant objects. It is a record written in motion. At the center of that record stands Neptune. As a major planet, Neptune has enough gravitational influence to affect smaller bodies moving through nearby regions. That influence does not require physical contact. Gravity changes motion across distance, and even a relatively small adjustment can matter when it happens repeatedly. Imagine two objects following separate paths around the Sun. If their movements bring them into the same general arrangement again and again, the timing of their gravitational interactions can become significant. Instead of receiving random influences, the smaller object encounters a repeating pattern. This is the basic idea behind orbital resonance. Resonance does not mean two objects collide or remain beside each other. It means their orbital periods form a repeating relationship, so the timing of their positions follows an organized pattern. That repeated timing can help shape an object's path. A useful way to picture the idea is to think about a gentle push delivered at regular intervals. One push may have little effect. Repeated pushes that arrive with consistent timing can gradually produce a more noticeable result. The comparison has limits, because gravitational interactions follow orbital mechanics rather than the simple movement of an everyday object. But it captures the important point: timing matters. In the outer solar system, some smaller bodies move in repeating relationships with Neptune. Their orbits are not independent of the planet's presence. They reflect a long history of gravitational influence, arranged through recurring patterns. This does not mean Neptune pulled every nearby object into the same path. Different bodies respond differently depending on where they formed, how they moved, and how their orbits related to the planet. Some can remain in comparatively stable arrangements. Others can be redirected onto more extended paths. The result is a population with distinct orbital families, rather than a simple uniform ring. But resonance alone does not explain how those relationships first developed. If the outer solar system had always looked exactly as it does today, some observed arrangements would be harder to understand. The present positions of the major planets may not tell the complete story of where those planets once moved. That possibility changes the investigation. A planet does not need to remain in precisely the same orbital location throughout the entire history of a planetary system. Interactions among planets and smaller bodies can alter orbital arrangements over long periods. This gradual change is known as planetary migration. Migration does not mean a planet suddenly raced outward through space or followed a simple straight route. It refers to changes in the size and shape of a planet's orbit as gravitational interactions redistribute motion within the system. When astronomers examine the current structure of the outer solar system, they can compare those patterns with models of how the planets and smaller objects might have interacted earlier. Some models suggest that Neptune's position changed during the early development of the solar system. As its orbit shifted, the regions influenced by its gravity shifted as well. That would matter enormously for nearby small bodies. An object that once moved without a strong repeating relationship with Neptune might enter one as the planet's orbital position changed. Once captured into a stable resonance, the object could retain a lasting connection to Neptune's movement. Other bodies would experience different outcomes. Some could be pushed onto more stretched orbits. Some could move into different regions. Some might remain comparatively undisturbed, preserving a record of conditions that other objects no longer reflect. The important point is that the present arrangement need not represent the original arrangement. The frontier may have been reorganized. Consider what that means for the objects we observe today. A distant body is not necessarily sitting exactly where it first formed. Its current position may reflect a sequence of gravitational changes that carried it away from an earlier location. Its orbit becomes a surviving trace of that history. This helps explain why scientists treat orbital patterns as evidence rather than merely describing the outer solar system as a collection of frozen remnants. The remnants have been sorted. Some appear in stable groups. Some occupy repeating relationships with Neptune. Others follow paths suggesting that stronger interactions change their original motion. Together, those differences provide clues about how the system developed. But there is an important boundary between what scientists observe and what they reconstruct. The orbits themselves can be measured. Astronomers can track the positions of distant objects and calculate the paths those objects follow around the Sun. They can identify patterns, compare groups, and determine whether certain movements maintain repeating relationships with Neptune. The ancient history behind those patterns cannot be observed in the same direct way. No telescope can look backward and watch the early planets rearranging their orbits. Instead, researchers use models to test which past interactions could produce the distribution visible today. A successful model can explain multiple features of the present system. It might show how a changing planetary orbit creates stable resonances, redirects smaller bodies, or leaves different populations in different regions. If the resulting patterns resemble the observed ones, the model gains support. But resemblance is not the same as a direct recording. More than one early history may explain some of the same evidence. Details can change as additional objects are discovered or as models improve. The broad influence of gravity is clear, while the exact sequence of ancient events remains a reconstruction. That distinction does not weaken the investigation. It makes the investigation more precise. We know that the outer objects have particular orbits. We know Neptune's gravity influences bodies around it. We can identify repeating orbital relationships. From those observations, scientists build explanations for how the frontier acquired its present structure. The strongest account is not that the outer solar system remained untouched. It is that a changing system left behind an organized collection of survivors. Some objects remained in stable regions. Some became connected to Neptune through resonance. Others were displaced or redirected as the planetary architecture evolved. The frontier beyond the last planet is therefore not separate from the history of the planets. It is part of that history, preserving evidence of interactions that continued long after the first simple picture of a planetary lineup would suggest. Yet an orbit can only tell us certain things. It can reveal movement, gravitational influence, and the possible consequences of earlier interactions. It cannot, by itself, show the detailed shape of a distant body or reveal what its surface looks like from close range. A mathematical path is not the same as a physical encounter. To understand how these remote worlds actually formed, scientists need more than the outline of their orbits. They need evidence that comes from approaching individual objects closely enough to study their physical structure. That kind of evidence is rare. The distances are enormous, and the known population extends across a region far larger than any single spacecraft can survey directly. Most bodies remain distant points whose movements tell us more than their appearances. But a small number have been seen differently. When a spacecraft passes close enough to examine an outer world, it can reveal details that orbital patterns alone cannot provide. The shape of a body, the structure of its surface, and the way its parts fit together can offer new clues about its history. Those clues do not replace the evidence written in orbits. They add another layer. The evidence grows stronger when both perspectives work together. The question now is what happened when distant points beyond Neptune stopped being points and became worlds observed up close. For most of human history, the distant bodies beyond Neptune could only be understood from far away. Their movement could be measured, their brightness could be tracked, their orbits could be compared with the paths of other objects. But distance concealed their physical character. A body seen as a faint point could represent many different possibilities. It might be relatively smooth or deeply uneven. Its surface might preserve old material or show evidence of change. Two objects following broadly similar paths might look completely different when examined closely. An orbit could reveal where a body traveled. It could not reveal everything that body had experienced. That distinction became clearer when the New Horizons spacecraft approached Pluto. Before the encounter, Pluto was already known as a distant world orbiting beyond Neptune. Its classification had changed, and astronomers understood that it belonged to a broader population rather than standing alone at the end of a planetary sequence. Yet its actual appearance remained difficult to resolve. In 2015, New Horizons passed close enough to transform that distant point into a visible world. The result was not the simple frozen object that an observer might have imagined from its small size and great distance. Pluto displayed a complex surface. Different regions showed different appearances, and the world possessed an atmosphere. These observations revealed a body that could not be reduced to its label or its position in a diagram. Calling Pluto a dwarf planet had described its relationship with the surrounding population. It had not explained the details of the world itself. That difference is important. A scientific classification can tell us how an object compares with others, but it does not determine how interesting its surface will be. Nor does distance from the Sun automatically mean that a world must appear simple or unchanged. Pluto demonstrated that the outer frontier contains places with distinct physical identities. The flyby also changed the quality of the evidence. Earlier observations had established Pluto's existence, orbit, and general position within the outer solar system. The spacecraft encounter added information gathered much closer to the object itself. Instead of relying only on a faint, distant image, scientists could examine features that were previously impossible to distinguish clearly. This did not mean every question about Pluto had been answered. A flyby provides a limited opportunity to observe a world. It does not amount to a complete exploration of every location or every process. But even a brief close encounter can change what scientists are able to ask. The point of interest moves from whether an object exists to what kind of place it actually is. Pluto provided one version of that transformation. Another came from a much smaller body farther along the spacecraft's journey. In 2019, New Horizons encountered Arrokoth. Unlike Pluto, Arrokoth was not already familiar to generations of people through classroom diagrams. Its significance rested less on cultural recognition and more on the physical clues preserved in its unusual shape. Arrokoth consists of two connected lobes. The object is often described as a contact binary, meaning that two formerly separate parts are now joined together as one body. That shape immediately raises a question. How did the two parts come together without destroying the structure that remains visible today? A violent collision would generally be expected to produce a very different outcome from a gentle meeting. If two bodies struck each other with enough force, their original forms could be heavily damaged or disrupted. Arrokoth's connected appearance supports a different interpretation. Its two components may have approached one another slowly enough to join without being shattered. This idea is described as gentle assembly. The physical shape is directly observed. The explanation of how the shape formed is an interpretation based on that evidence. Keeping those two ideas separate matters. Scientists can see that the body has two joined lobes. They use that observation to evaluate which formation scenarios are consistent with the structure. The shape supports the possibility of a relatively calm joining process. It does not provide a complete recording of the event. Nor does it prove that every small object beyond Neptune formed in exactly the same way. Arrokoth is one body in a much larger population. Other objects may have experienced different conditions, different interactions, or different histories. Its value comes from providing a concrete example of what the early outer solar system may have allowed. The encounter also shows why direct observation can complement orbital studies. An orbit tells us how a body moves around the Sun. A close image can reveal whether that body contains structural clues about how its parts assembled. These forms of evidence answer different questions. The movement of an object may indicate how larger planets influenced its path. The object's shape may preserve evidence of how smaller pieces came together before or during that wider history. Neither perspective alone gives the complete picture. Together, they make the frontier more understandable. Pluto and Arrokoth illustrate this contrast in different ways. Pluto appeared as a larger distant world with a complex surface and an atmosphere. Arrokoth appeared as a smaller body whose connected shape offered clues about a possible formation process. They belong to the same broad outer region, yet they are not interchangeable. That difference challenges any attempt to describe the Kuiper Belt as a single type of place filled with identical frozen objects. The region contains diversity. Some bodies are rounded worlds. Some are smaller and irregular. Some preserve structures that suggest relatively gentle assembly. Their shared distance does not erase the differences in their physical histories. But the same discoveries also reveal a serious limitation. Too close encounters cannot describe an entire population. New Horizons followed a particular route through the outer solar system. It did not visit every distant body, map every orbital family, or determine the physical character of everything beyond Neptune. Pluto and Arrokoth provide valuable evidence because they were examined closely. They do not provide a complete census. This is especially important when moving from a single example to a wider conclusion. Arrokoth's shape may support one formation model, but another distant object could preserve evidence of a different process. Similarly, Pluto's complexity does not mean that every dwarf planet or smaller body has an identical surface or atmosphere. The evidence becomes strongest when each observation is connected to the question it can actually answer. Pluto shows that a distant dwarf planet can possess a complex physical identity. Arrokoth shows that a small outer object can preserve a structure consistent with gentle assembly. Neither encounter defines the full boundary of the region they inhabit. And neither tells us whether the familiar map of the outer solar system includes all the objects that exist farther away. A spacecraft can reveal remarkable detail about whatever lies directly along its path. Everything outside that narrow route remains dependent on other observations. Every close encounter adds depth to the map, but it also reveals how incomplete that map remains. The more clearly one object can be examined, the more obvious it becomes that countless other bodies still exist beyond the narrow reach of any single journey. That leaves a larger question unresolved. If the worlds examined closely represent only a tiny part of the population beyond Neptune, how far does that population really extend? The main region of the Kuiper Belt provides one useful description, but the objects moving through the outer solar system do not all remain within a neat ring. Some follow paths that carry them into more distant territory. Others occupy orbits that seem difficult to explain through the simplest picture of a clearly bounded belt. These patterns suggest that the familiar frontier may not have the clean outer edge that diagrams imply. To understand what lies farther out, the investigation must move beyond the world seen up close and return to the objects whose paths carry them into less familiar regions. The next clues are not found in a single surface or a connected pair of lobes. They appear in orbits that refuse to stay where the map says the belt should end. A boundary on a diagram can make a region look more definite than it really is. Draw a line around the main part of the Kuiper Belt, and it becomes tempting to imagine that the population ends where that line appears. Inside the boundary, there are icy bodies. Outside it, there is something else. The actual outer solar system is less orderly. The familiar estimate of about 50 astronomical units describes the approximate outer extent of the belt's main population. It does not mark a wall, an empty gap, or a point beyond which no smaller bodies can exist. The number of objects may decline. Their distribution may change. But an orbit does not have to respect the edge of a simplified illustration. Some bodies follow paths that carry them well beyond the region normally associated with the main Kuiper Belt. Their existence turns a narrow-looking frontier into a broader collection of overlapping populations. One of those populations is called the scattered disk. The name describes objects whose orbits have been shaped by gravitational interactions that send them along more extended paths. Rather than remaining within a relatively confined part of the outer system, these bodies can travel through a wider range of distances from the Sun. Their orbits are stretched. That means an object can come nearer the planetary region during one part of its journey and move much farther away during another. Its location at any single moment does not reveal the full territory covered by its orbit. This distinction matters when imagining the outer solar system. An object photographed at one distance might spend much of its time somewhere else. Another body could remain difficult to detect because it moves slowly through a remote portion of its path, far from the region where observations are easiest. The scattered disk is therefore not simply another neat ring placed after the Kuiper Belt. It overlaps with the broader outer population while extending into regions the main belt does not fully describe. Neptune remains relevant because gravitational encounters can influence how these orbits develop. But the result is not a uniform collection of objects moving together. It is a population whose members follow individual paths through a more dispersed frontier. Beyond these scattered objects, astronomers have also identified bodies whose orbits present a different kind of puzzle. They are often described as detached objects. The term refers to their relationship with the known giant planets, especially Neptune. These bodies remain far enough away that their present orbits cannot be explained as easily through ordinary close interactions with Neptune today. That does not mean they are disconnected from the Sun. They still orbit it. What appears detached is their relationship with the familiar planetary influences that help explain many other distant orbits. One of the clearest examples is Sedna. Sedna follows a highly extended path around the Sun, but even its closest approach remains far beyond Neptune. That nearest point is approximately 76 astronomical units from the Sun. Compare that with Neptune's orbit at roughly 30 astronomical units. Even when Sedna comes as close to the Sun as its orbit allows, it remains in a region far outside Neptune's immediate neighborhood. For the rest of its journey, Sedna moves farther away. This creates a difficult question. If an object never approaches the known giant planets closely enough for their present positions to explain its path easily, what placed it on that orbit? The observation itself is clear enough to state carefully, Sedna exists, its orbit can be calculated, and its closest approach remains unusually distant. The explanation is less certain. An unusual orbit can preserve evidence of earlier events, distant gravitational influences, or conditions that differ from the present arrangement of the solar system. But an observed path does not automatically identify one unique cause. More than one history may fit the available evidence. That is why Sedna should not be treated as proof of any single unseen object or dramatic event. It is a clue. Its importance comes from revealing that the outer system contains bodies whose behavior cannot be reduced to the simplest picture of a belt ending near 50 astronomical units. The frontier continues, but it becomes harder to describe with familiar categories. There are also other signs that the outer region may contain more material than a simple textbook boundary suggests. New Horizons has measured dust while traveling through the outer solar system. These measurements provide information about tiny particles that are difficult to detect directly from Earth. Dust does not provide the same evidence as a photographed world. Its significance depends on how scientists interpret the measurements and compare them with expectations about the material present in that region. If more dust is detected than a particular model predicts, several possibilities may need to be considered. The result could suggest that distant objects, collisions, or additional material contribute to an environment more extended than expected. But a dust measurement does not automatically confirm a new belt. It does not reveal a complete population of unseen worlds, and it does not prove that a specific outer structure has been discovered. The responsible conclusion is narrower. Some measurements suggest that the outer solar system may contain material beyond the simplest description of the familiar Kuiper Belt. The meaning of that evidence remains under investigation. This distinction between measurement and interpretation becomes increasingly important with distance. Objects become harder to detect. Their paths may take them far beyond the areas most carefully observed. Evidence can arrive through faint points of light, calculated orbits, or tiny impacts on a spacecraft instrument. Each method reveals part of the picture. None supplies a finished map. A region can become less populated without becoming empty, and a population can become harder to observe without disappearing. These are different problems. One concerns what exists in the outer solar system. The other concerns how much of that territory our instruments and models can currently reveal from limited available evidence. The main Kuiper Belt remains a useful description of the first broad population beyond Neptune. The scattered disk extends that picture through elongated orbits. Detached objects show that some distant bodies remain beyond straightforward explanation by the present giant planets. Dust measurements add another possibility. The material associated with these remote populations may not stop where a simplified diagram suggests. Together, these observations replace the idea of a sharp outer line with a more gradual and uncertain frontier. But uncertainty does not mean that every proposed explanation deserves equal confidence. A distant object can be real, while the story told about its orbit remains speculative. A dust signal can be measured accurately, while its larger meaning remains open to debate. The evidence must come first. The explanation has to earn its place. Sedna and other distant bodies raise a question that becomes more difficult to ignore as their orbits are compared. Why do some objects follow paths that seem unusually arranged? Could the known planets explain those patterns through earlier changes in the solar system? Could the available observations be incomplete? Or might another gravitational influence exist farther out? One possibility has attracted particular attention. If a large undiscovered planet occupied a distant orbit, its gravity could potentially affect smaller bodies moving through the outer frontier. But proposing such an object is not the same as finding it. Before accepting that possibility, we need to examine what the orbital evidence actually shows, what it does not establish, and why the search for another planet remains uncertain. The possibility of another planet begins with a pattern. Far beyond Neptune, Some distant objects follow orbits that appear to share unusual features. Their paths are stretched, and certain aspects of those paths seem to line up more than a completely random distribution might suggest. That observation raises an obvious question. Could something farther out be influencing them? Gravity can reveal the presence of an object even when that object cannot be seen directly. If several smaller bodies respond to the same unseen influence, their movements may carry evidence of whatever is affecting them. This is the idea behind the Planet 9 hypothesis. The proposal suggests that a large, distant planet could exist beyond the familiar planetary region. Its gravity might gradually shape the orbits of smaller objects moving through the outer solar system. The idea is not based on a photograph of a new planet. No confirmed observation has shown such a world moving against the background sky. No spacecraft has visited it. No complete orbit has been established through direct tracking. What exists is a proposed explanation for certain orbital patterns. That difference must remain clear from the beginning. A pattern in data is an observation. A planet proposed to explain that pattern is a hypothesis. Confirmation would require stronger evidence than the suggestion itself. To understand why the hypothesis attracts attention, consider what happens when several distant objects appear to follow related paths. If their orbits were shaped independently, their orientations might be expected to vary more widely. A noticeable grouping can therefore invite questions about whether a shared influence helped organize them. A distant planet offers one possible mechanism. Its gravity could act over long periods, gradually affecting smaller bodies without requiring them to collide with the planet or pass immediately beside it. Repeated influence could help maintain patterns that otherwise seem difficult to explain. This does not mean the proposed planet has already been detected through gravity in the same way that a known object can be measured directly. The interpretation depends on how convincing the pattern actually is. That is where the problem becomes more complicated. The outer solar system is difficult to observe. Its objects are faint, far away, and spread across a vast region. Telescopes cannot watch every direction with equal sensitivity at all times. The bodies that astronomers discover therefore depend partly on where they look. This creates the possibility of survey bias. A survey is an organized attempt to search a particular part of the sky. Its results are shaped by the locations observed, the sensitivity of the instruments, and the conditions under which the search takes place. If some regions receive more attention than others, discoveries may cluster there even when the real population is distributed differently. Imagine trying to understand an entire landscape while examining only a few illuminated patches. The objects found inside those patches may appear grouped simply because the surrounding darkness has not been searched equally. The grouping would be real within the available observations, but its meaning would remain uncertain. The same issue can affect distant orbital studies. Astronomers do not observe every object along its entire path. They detect objects when those bodies are bright enough, favorably positioned, and located within the regions a survey can examine. That means the visible sample may not represent the complete population. An apparent alignment could reflect a genuine physical influence. It could also reflect the limits of observation. Separating those possibilities requires careful analysis of how each object was discovered and which parts of the sky were effectively searched. The number of known distant objects also matters. When the sample is small, chance arrangements can appear more significant than they truly are. A few similar paths may look striking until more objects are found and the broader distribution becomes visible. A larger sample can strengthen a pattern. it can also make the pattern disappear. This is why the Planet 9 question cannot be settled by pointing to a handful of unusual orbits and declaring the mystery solved. Scientists must ask whether the grouping remains after observational bias is considered. They must examine whether independent surveys find similar patterns. They must test whether other explanations could produce the same result. Those alternatives matter because an observed orbit does not preserve a label identifying its cause. The outer solar system has a long gravitational history. Earlier planetary movements, interactions among distant bodies, or other dynamical processes may help explain some features without requiring a newly discovered planet. The evidence may also reflect more than one influence. A pattern produced by a combination of processes can be difficult to separate into individual causes, especially when observations remain incomplete. This does not mean the distant planet idea should be dismissed. It means the idea must compete with other explanations. This process is not a disagreement between curiosity and caution. Curiosity identifies the unusual arrangement and asks what might explain it. Caution checks whether the arrangement remains unusual after the limits of the search are understood. Both are necessary. Without curiosity, a real distant influence could be overlooked. Without caution, an incomplete collection of observations could be mistaken for proof of a world that has never been found. The same evidence must therefore be examined from more than one direction before any interpretation becomes persuasive. A useful scientific hypothesis does more than sound plausible. It offers a mechanism that can be tested against observations and potentially ruled out if the predicted evidence fails to appear. Planet 9 remains interesting because it provides a concrete possible explanation for certain unusual orbital arrangements. But scientific interest is not the same as scientific confirmation. The proposed planet would also be difficult to find if it exists. A distant object receives less sunlight than a body closer to the sun, and any reflected light must travel a great distance before reaching observers. The result is a target that could appear extremely faint. Its exact location would also be uncertain. A hypothesis can suggest broad regions where a search might be useful without identifying a single point in the sky. Searching for a faint object across a large area requires time, sensitivity, and repeated observation. Even a real planet would not necessarily announce itself immediately. But difficulty is not evidence of existence. The fact that an object could remain hidden does not establish that it is actually present. That distinction prevents uncertainty from turning into a story that cannot be challenged. If the planet exists, direct detection should eventually provide a clearer test. Observers would need to identify a candidate, track its movement, and determine whether its orbit and gravitational influence match the proposed explanation. Additional discoveries of distant smaller bodies could also help. If newly detected objects continue to display the predicted patterns across independent surveys, the case for a shared influence may become stronger. If the alignment weakens as the sample grows, or if survey bias accounts for the apparent grouping, the explanation may become less convincing. Both outcomes would improve the map. A confirmed planet would expand the known planetary system. A rejected hypothesis would clarify how observation and gravitational history can create misleading appearances. The value of the investigation does not depend on obtaining the most dramatic answer. It depends on learning which answer the evidence supports. At present, the responsible conclusion is straightforward. Some distant objects follow unusual orbits. Researchers have proposed that an unseen planet might help explain certain patterns. No such planet has been confirmed. The observation, the interpretation, and the proposed object remain separate. That separation also protects the larger question guiding this journey. Suppose another planet were eventually found beyond Neptune. Its discovery would change which world deserved to be called the outermost recognized planet. It would expand the familiar list and force another revision of the diagrams used to describe the solar system. But it would not automatically reveal where the solar system ends. A planet would still be an object moving within a larger environment. Its orbit would describe one part of the Sun's domain, not every physical boundary associated with our star. The search for another world, therefore, cannot settle the problem of the final frontier. It can only extend the planetary map. To find a different kind of boundary, we have to stop looking exclusively for large objects. The Sun influences its surroundings through more than gravity. It also sends material outward, creating an environment that can extend far beyond the recognized planets. That environment cannot be understood simply by counting worlds or calculating the orbits of distant icy bodies. It must be studied through the particles and conditions present in space itself. Unlike Planet 9, whose existence remains uncertain, this outer environment has been measured by spacecraft. The evidence does not depend on discovering another planet. It comes from detecting a change in the nature of the space surrounding the Sun. And that leads to a different question. How can a star create a boundary in a region that appears almost completely empty? The Sun appears to rule the solar system through light and gravity. Its light illuminates planets and smaller bodies. Its gravity holds those objects in orbit. Yet the Sun also influences the surrounding space in another way. It continually releases matter. The material flowing outward from the Sun is called the solar wind. It is not wind in the ordinary sense. There is no atmosphere carrying moving air across the solar system. The solar wind consists mainly of electrically charged particles. These particles escape from the Sun and stream outward in every direction. Close to the Sun, their presence is stronger and their motion is dominated by the star that released them. As they travel farther away, they spread through an increasingly large volume. This flow creates an environment around the Sun. That environment is known as the heliosphere. It can be imagined as an enormous region filled and shaped by material coming from our star. The word sphere provides a useful starting picture, but it should not be taken too literally. The heliosphere is not a perfectly round shell centered on the Sun. It is a changing region formed through interaction. Outside it lies material associated with the space between stars. That surrounding interstellar environment also contains particles, magnetic fields, and pressure. The solar wind pushes outward. The surrounding medium pushes back. The boundary develops where these influences meet. This does not create a hard surface. There is no solid barrier that a spacecraft can strike, and there is no visible wall hanging in the darkness. Instead, conditions change across a broad outer region. To understand that change, it helps to follow the solar wind as it moves away from the Sun. Nearer the star, the charged particles travel outward rapidly. They carry the influence of the Sun across distances far beyond the planets. But the flow cannot continue unchanged forever. As it encounters resistance from the surrounding interstellar environment, the solar wind begins passing through outer zones. The first major transition is called the termination shock. The name can sound more violent than the process needs to appear. It refers to a region where the outward solar wind slows sharply as it responds to conditions farther from the Sun. The solar wind does not terminate there. It continues outward, but its speed and behavior have changed. Beyond the termination shock lies the heliosheath. This is the outer part of the heliosphere, where the solar wind has slowed, but has not yet reached the final boundary of its dominance. The region is not merely an empty gap between two lines. It is part of the interaction between material from the Sun and material beyond the Sun's particle environment. Farther outward lies the heliopause. The heliopause marks the boundary where the solar wind is no longer the dominant particle flow, and the surrounding interstellar environment becomes more influential. This makes it a meaningful edge. If the solar system is defined as the region controlled by the Sun's outward particle flow, the heliopause provides a physical boundary for that definition. But even this edge is more complicated than a line drawn at one permanent distance. The Sun changes. Its activity varies, and the solar wind does not always leave the star under identical conditions. The surrounding interstellar medium can also vary. Because the heliopause is created through a balance between interacting environments, changes in either side can alter its location or shape. The boundary can move. It can also have an uneven form. A measurement made along one outward direction does not automatically reveal the precise distance of the heliopause in every other direction. A spacecraft crosses the boundary at a particular place and time. That crossing provides direct evidence about the conditions along its path. It does not produce a complete three-dimensional map. The heliopause may also be porous rather than perfectly sealed. Particles and influences can cross or interact near the boundary in ways that do not match the image of two completely separated regions. This is why the heliosphere should be understood as a dynamic system. It is made by continuing flows and pressures, not constructed from fixed material. That creates an unusual challenge for exploration. How can a spacecraft know that it has crossed something invisible, uneven, and capable of moving? The answer must come from measurements. A spacecraft carries instruments that respond to the particles, fields, and plasma around it. Plasma is matter in which charged particles move as an electrically active environment. The solar wind itself is plasma. So is much of the material involved in the interaction near the heliopause. While a spacecraft remains within the solar wind-dominated region, its instruments detect particle populations associated with the Sun. As the spacecraft approaches and crosses the outer boundary, those populations should change. Particles originating from the Sun can decline. At the same time, galactic cosmic rays can become more common. These are high-energy particles arriving from beyond the heliosphere. The change is meaningful because the heliosphere affects which particle populations dominate the local environment. A spacecraft can therefore detect a transition without photographing it. It can observe that one kind of particle has decreased while another has increased. Magnetic conditions provide another source of information. Charged particles and magnetic fields are connected, so instruments can examine how the surrounding field behaves as the spacecraft moves through different regions. But one measurement alone may not provide a simple answer. A magnetic field may not change in exactly the way an early model predicts. A particle count may fluctuate before settling into a clearer pattern. The boundary itself can contain transition layers rather than behaving like a perfectly sharp dividing line. Scientists must compare several signals. Plasma density is especially valuable. Density describes how much material is present within a given volume. Even though both the heliosphere and interstellar space are extremely sparse by everyday standards, their plasma conditions are not identical. A change in plasma density can help identify which environment surrounds the spacecraft. When particle measurements, cosmic ray levels, magnetic observations, and plasma evidence are considered together, they can provide a stronger conclusion than any one signal could support by itself. This approach reflects a broader principle used throughout the outer solar system. An invisible object or boundary can be studied through its effects. The Kuiper Belt became visible as a population through many detected bodies. A possible distant planet is considered through orbital patterns, though it remains unconfirmed. The heliopause can be identified through coordinated changes measured directly by spacecraft moving through it. These situations do not carry equal certainty. The crucial difference is that a spacecraft can sample the environment on both sides of the heliopause. It can record conditions before the transition and compare them with conditions afterward. That turns a proposed boundary into something physically testable. Yet crossing the heliopause answers only one version of the larger question. It shows where the sun's outward particle flow stops dominating the surrounding medium. It does not show where every object orbiting the sun disappears. It does not establish where the sun's gravity becomes irrelevant. And it does not mean that all traces of solar influence vanish immediately beyond the crossing. The heliopause is therefore both a genuine edge and an incomplete answer. It marks the end of one solar environment while leaving other definitions of the solar system untouched. This is what makes the boundary so important. It gives the journey beyond Neptune a frontier that spacecraft can actually reach and measure, even though that frontier is not the final edge under every scientific definition. For decades, two spacecraft traveled outward while the solar wind around them gradually changed. They passed through regions that had never been sampled directly from within. Their instruments watched the balance of particles shift as the sun's wind weakened against the surrounding interstellar medium. Eventually, those measurements indicated that the spacecraft had entered a different environment. There was no flash and no visible line. The evidence arrived through particles, plasma, and fields. To understand what those spacecraft crossed, we must examine how several quiet changes combined into one historic conclusion. Voyager 1 had been traveling for about 35 years when the surrounding space began to change in a decisive way. The spacecraft did not approach a visible surface. Nothing appeared ahead of it. There was no moment when a camera could photograph the edge of the sun's particle environment. The crossing had to be reconstructed from what Voyager's instruments detected around the spacecraft. On 25 August 2012, Voyager 1 crossed the heliopause at a distance of approximately 122 astronomical units from the Sun. That placed the crossing more than 4 times farther from the Sun than Neptune's orbit. The distance alone did not prove that the boundary had been crossed. The heliopause is not defined by reaching a fixed number of astronomical units. It is defined by a change in the surrounding physical environment. The first important evidence came from particles associated with the Sun. Before the crossing, Voyager traveled through a region still dominated by material originating within the heliosphere. As it approached the boundary, the number of these solar origin particles declined. That decrease suggested that the spacecraft was leaving the environment filled by the Sun's outward flow. At nearly the same time, another particle population increased. Galactic cosmic rays became more common. These high-energy particles arrive from beyond the heliosphere. The Sun's particle environment affects how easily they enter its inner regions, so their increasing presence indicated that Voyager was moving into space more strongly connected to the surrounding interstellar environment. The two changes supported each other. One population associated with the Sun decreased. Another arriving from outside the heliosphere increased. Together, they provided strong evidence that Voyager had entered a different region. Yet the interpretation was not immediately simple. Scientists also watched the magnetic field around the spacecraft. Some expectations suggested that crossing the heliopause might produce a clear change in the field's direction. The observed behavior did not match the simplest version of that expectation. The magnetic field remained oriented in a way that complicated the first interpretation of the crossing. This did not cancel the particle evidence. It showed why one measurement should not carry the entire conclusion. An actual boundary can behave differently from a simplified model. The heliopause is shaped by interacting plasma and magnetic conditions, and the transition need not produce every expected signature in the clearest possible form. Scientists therefore had to compare the available signals rather than selecting only the most convenient one. The particle changes were striking, but another form of evidence was needed to strengthen the case. That evidence came from plasma density. Voyager 1 could not rely on every instrument in the same way it had earlier in its mission, but disturbances moving through the surrounding plasma allowed researchers to determine information about the density of that environment. The result indicated that the plasma around Voyager was denser than the plasma found within the outer heliosphere. That higher density was consistent with the local interstellar medium. This was a crucial confirmation. Particle counts had shown that the balance of populations changed. Plasma evidence showed that the physical environment itself matched what scientists expected beyond the heliopause. The crossing was therefore supported by several connected observations. Solar origin particles declined. Galactic cosmic rays increased. Plasma density rose to levels associated with interstellar space. The magnetic evidence remained more complicated, reminding scientists that the boundary was not a simple wall with every property changing in the same way at the same instant. Taken together, the measurements supported the conclusion that Voyager 1 had crossed the outer edge of the solar wind-dominated heliosphere. For the first time, a human-made spacecraft was directly sampling the very local interstellar medium. The achievement was easy to describe dramatically, but its scientific meaning required care. Voyager 1 had entered interstellar space in a heliophysical sense. It had crossed the boundary where the surrounding plasma was no longer dominated by the solar wind. That did not mean the spacecraft had passed beyond everything connected to the Sun. It remained under the Sun's gravity. It had not reached the most distant populations of bodies thought to orbit our star. It had crossed one real boundary, not every possible boundary. The distinction became clearer when Voyager 2 approached the heliopause along a different path. Voyager 2 crossed in November 2018 at approximately 119 astronomical units from the Sun. This second crossing mattered for more than historical repetition. One spacecraft can sample only one narrow route through a vast, changing boundary. A second crossing provides another location, another time, and another set of measurements. Voyager 2 did not cross at exactly the same distance as Voyager 1. The difference was not evidence that one spacecraft had measured the boundary incorrectly. It was consistent with the heliopause being dynamic. The boundary responds to changing solar conditions and to interaction with the surrounding interstellar medium. Its position can vary, and its shape need not place every outward direction at the same distance from the Sun. Voyager 2 also carried working instruments that offered a valuable second view of the transition. Its observations confirmed the broad pattern of leaving a solar wind-dominated environment and entering the local interstellar medium. Two crossings could still not create a complete map. The spacecraft traveled outward along different but limited paths. They did not surround the heliosphere, and their measurements could not reveal every curve, layer, or change across the boundary. But their agreement on the basic transition was powerful. Voyager 1 established that the particle and plasma environment had changed near 122 astronomical units along its route. Voyager 2 detected a corresponding transition near 119 astronomical units along another route and at another time. The combined evidence turned the heliopause from a theoretical outer feature into a boundary sampled directly in two places. The time between the two events also protected the conclusion from depending on one brief condition. Voyager 1 crossed in 2012. Voyager 2 reached its boundary more than 6 years later. During that interval, the Sun and the surrounding interface continued to change. Even so, both spacecraft recorded the same essential transfer from a region shaped by solar particles to one shaped by interstellar plasma. The details differed because the paths, instruments, locations, and times differed. The meaning remained consistent. This is how separate measurements strengthen a scientific conclusion. They do not need to be identical in every detail. They need to support the same explanation after their differences are understood. In this case, the differing distances helped expose the boundary's changing nature, while the shared environmental transition confirmed what the boundary represents. This is one of the strongest answers available to the question of what happens beyond the last planet. Travel far beyond Neptune, continue through the region influenced by the solar wind, cross the termination shock and heliosheath, and eventually the surrounding plasma changes. Solar particles lose their dominance. Interstellar conditions take over. A spacecraft enters the space between stars. But the phrase space between stars can be misleading if it suggests complete emptiness or total separation from the Sun. Voyager did not enter a perfect vacuum. Its instruments continued to detect particles, plasma, magnetic conditions, and cosmic rays. The environment changed, but measurement did not end. Nor did the crossing remove the spacecraft from every solar relationship. The Sun remained behind it as the central gravitational body of the system from which Voyager had departed. Distant objects thought to orbit the Sun could exist far beyond the spacecraft's present path. Calling Voyager interstellar is therefore accurate when the term identifies the surrounding medium. Calling it completely beyond the solar system would require choosing a much narrower definition of the system than many scientists use for its material and gravitational extent. This is not a contradiction. A traveler can cross one kind of border while remaining inside another. The Voyager crossings show why the solar system cannot be reduced to one final line. The heliopause is genuine, measurable, and physically important. It separates two different particle environments. Yet it does not separate everything belonging to the Sun from everything belonging to the galaxy. What Voyager left was the region dominated by the solar wind. What it entered was the very local interstellar medium. The next step is to understand what that phrase describes. The space outside the heliopause is thin beyond ordinary experience, but it is not nothing. It contains matter and fields capable of shaping the boundary Voyager crossed. Those conditions surround the heliosphere and reveal how our star meets the wider galaxy. Voyager's achievement was not that it reached the end of all solar influence. It was that, After decades of travel, it became the first direct messenger from the environment on the other side of the sun's invisible bubble. Beyond the heliopause, Voyager did not enter an absence. It entered a different kind of presence. The space surrounding the spacecraft remained extraordinarily thin. No ocean of gas appeared. No visible clouds gathered around its instruments. To an ordinary observer, the darkness would still have looked almost unchanged. Yet the material within that darkness had a different origin and a different relationship with the sun. This environment is called the very local interstellar medium. The name describes the immediate portion of the material found between stars, specifically the region surrounding the sun and its heliosphere. It is not a distant destination on the opposite side of the galaxy. It begins just beyond the boundary, where the solar wind no longer dominates. The word medium matters. It means there is something there. Interstellar space contains particles, even though they are spread across enormous distances. Some carry electric charge, others remain electrically neutral. Magnetic fields extend through the region, while small dust particles and cosmic rays contribute to the wider environment. None of these components needs to be crowded to have physical consequences. The charged particles form plasma. Plasma is familiar from the solar wind, but the plasma beyond the heliopause belongs to a different environment. Its properties reflect the surrounding interstellar region rather than the outward flow directly controlled by the sun. That distinction helped reveal that Voyager had crossed a boundary. The spacecraft moved from one particle environment into another, even though both would seem almost empty by ordinary human standards. Neutral atoms provide another part of the picture. An atom becomes electrically neutral when its positive and negative charges balance. Unlike charged particles, neutral atoms do not respond to magnetic fields in exactly the same way. That difference affects how they move through the outer regions surrounding the heliosphere. Some can travel through areas where charged particles follow more complicated paths. Their presence helps scientists understand how material from outside the solar wind interacts with the sun's broader environment. The magnetic field also matters. A magnetic field is not a visible object, but it influences the motion of charged particles. In the region around the heliosphere, magnetic conditions help determine how material behaves and how the boundary between environments takes shape. The field does not act alone. It works alongside the pressure and movement of particles arriving from outside the sun's immediate domain. Dust adds another component. These tiny particles are not large enough to make interstellar space resemble a crowded cloud. They are scattered through a region that remains exceptionally sparse. Yet their presence confirms that the space between stars is not simply a blank gap. Material exists there, and that material can interact with the environment formed by the sun. Cosmic rays complete another part of the local picture. These energetic particles travel through space and become more prominent outside the protective influence of the heliosphere. Their presence helps distinguish the environment beyond the boundary from the region farther inward. Together, plasma, neutral atoms, magnetic fields, dust, and cosmic rays form a physical setting. They do not create a place that looks busy. They create a place that behaves differently from the sun's particle-dominated surroundings. This distinction becomes clearer when considering pressure. Pressure does not require thick air or a solid surface. Even a very thin collection of particles can exert an influence when it extends across an enormous region and interacts with another flow. The solar wind moves outward. The surrounding interstellar medium resists that outward expansion. Their interaction shapes the heliosphere. If the surrounding medium were truly empty, there would be no comparable material pressing back against the sun's outward flow. The boundary crossed by Voyager exists because two sparse environments meet and influence each other. The emptiness is therefore only visual. Physically, the region is active enough to establish a frontier. This also means the sun does not exist inside an isolated pocket cut off from the rest of the galaxy. Its particle environment develops within a larger setting, and that setting affects the size, shape, and behavior of the heliosphere. Our star carries its influence outward. The surrounding galaxy answers with an environment of its own. Voyager's measurements provide an extraordinary view of this interaction, but they also expose the limits of what two spacecraft can discover. Each Voyager follows one outward path. Together, their observations offer direct evidence from two directions and two crossing locations. They cannot reveal the full three-dimensional shape of the heliosphere or show how every part of its boundary changes. The spacecraft were not designed as a complete survey of interstellar space. Their instruments provide valuable measurements, but their paths were established by earlier mission objectives. The information they return is therefore both historically important and geographically limited. A boundary surrounding the entire solar system cannot be fully understood from two narrow tracks. Scientists can compare spacecraft measurements with models and other observations, but major questions remain about the shape of the heliosphere, the structure of its outer layers, and the changing conditions in the local interstellar medium. A dedicated interstellar probe could approach those questions more directly. Such a mission has been studied as a way to investigate the outer heliosphere and the nearby environment beyond it, using instruments designed around those specific goals. The concept should not be confused with a spacecraft already making those measurements. It represents a possible future effort, not a completed mission or a guaranteed launch. Its value would come from examining the same broad frontier with tools and planning focused specifically on understanding the interaction between the sun and the surrounding interstellar material. That distinction reflects a larger truth about the current map. Voyager showed that the boundary is real. It did not complete the exploration of everything around or beyond it. The very local interstellar medium remains a region scientists can sample, model, and gradually understand, but not yet describe in perfect detail. What lies beyond the heliopause is therefore not an empty void. It is a thin environment containing matter, fields, and energetic particles. It surrounds the sun's protective bubble and helps determine where that bubble ends. Yet another complication remains. Entering the interstellar medium does not mean entering a region where the sun no longer matters. The spacecraft still travel within the reach of solar gravity. The particles around them may belong to the space between stars, but objects much farther away can remain associated with the sun through their orbits. The environment and the gravitational family do not end together. These observations also change the meaning of the word outside. Voyager is outside the region dominated by solar wind, but it has not escaped every relationship with the sun. The surrounding material identifies one environment. The continuing reach of gravity describes a different kind of connection. This creates a remarkable possibility. Far beyond Voyager, there may be a vast population of distant bodies moving around the sun through territory already filled with interstellar material. Those bodies would belong to the solar system, in one sense, while occupying space beyond the solar wind in another. No spacecraft has reached that distant population. No telescope has photographed it as a complete structure. Yet evidence for its possible existence has traveled inward, arriving not as a clear image, but through the paths of objects that return from the darkness. To understand how the solar system can continue beyond the boundary Voyager crossed, we must follow those clues toward a region that may be vastly larger than everything encountered so far. The first evidence for a distant cloud does not come from a photograph. It comes from visitors. Occasionally, icy bodies travel inward from the outer darkness and approach the warmer regions of the solar system. Their paths can be calculated, and those paths reveal something important about where they may have originated. These objects are long-period comets. Unlike bodies that return after comparatively short journeys, long-period comets follow enormous orbits that carry them far from the Sun. Some approach from directions that do not match the flattened arrangement of the planets or the Kuiper Belt. That difference raises a basic question. If these comets arrive from many directions, where were they before their inward journeys began? One proposed answer is a distant reservoir of icy bodies surrounding the solar system. This reservoir is called the Oort Cloud. The name comes from Jan Oort, who proposed the idea in 1950 while considering the origins of long-period comets. The proposal was not based on directly seeing a distant cloud. It was based on interpreting the paths of objects that had traveled inward. A comet's orbit can be used to reconstruct the broad direction and scale of its journey. When many long-period comets are considered together, their distribution suggests a source that is not confined to the same flattened region occupied by the major planets. That is why the Oort cloud is usually described as approximately spherical. The shape does not mean a solid shell surrounds the solar system. It does not mean icy bodies are packed together in a visible cloud. It means that the proposed population may occupy a broad range of directions around the Sun rather than remaining concentrated in a disk. Like other outer populations, the individual objects would be separated by enormous distances. The word cloud describes their overall distribution, not their visual appearance. Even if a spacecraft moved through part of the proposed region, the surrounding space would still appear overwhelmingly empty. What makes the Oort cloud extraordinary is not its density. It is its possible scale. The inner region may begin somewhere around 2,000 to 5,000 astronomical units from the Sun. These numbers are estimates, not measured boundaries. They describe where models suggest a distant comet reservoir could begin, based on the behavior of long-period comets and the gravitational history of the solar system. The outer extent is even less certain. Some estimates place it around 10,000 astronomical units. Others extend the possible population toward 100,000 astronomical units. The range is wide because no telescope has mapped the cloud directly. No spacecraft has traveled far enough to examine it in person. And the faint objects thought to occupy the region are extraordinarily difficult to detect individually. The uncertainty is therefore not a minor detail. It is a central feature of the scientific picture. The Oort cloud may extend the Sun's gravitational family far beyond the heliopause, but its precise dimensions remain unknown. To understand how such a population might have formed, we have to return to the early solar system. During its development, large planets interacted gravitationally with smaller icy bodies. Some of those bodies could have been thrown onto orbits, carrying them far from the region where the planets formed. Not every displaced object would necessarily escape the Sun completely. Some could remain loosely bound, traveling on enormous paths through the outermost regions of the system. Over time, influences beyond the immediate planetary neighborhood could alter those paths. The galaxy itself produces gravitational effects sometimes described as galactic tides. Passing stars may also disturb the orbits of distant bodies. These influences could help reshape an initially scattered population into a broader distribution surrounding the Sun. The process is reconstructed through models. Scientists do not possess direct observations showing ancient icy objects moving outward and forming a spherical reservoir. They compare the behavior of present-day comets with possible gravitational histories and evaluate which explanations fit the available evidence. The result is a scientifically supported inference, not a photographed structure. This distinction becomes especially important when describing the cloud's relationship with the rest of the solar system. The proposed objects would remain connected to the Sun through gravity, yet they could move through regions already occupied by interstellar material. A body does not need to remain inside the heliosphere to continue orbiting the Sun. The solar wind and the Sun's gravitational influence operate on different scales. That is why Voyager's entry into interstellar space does not imply that it has already reached the Oort Cloud. The spacecraft crossed the boundary of the solar wind-dominated environment. The proposed Comet reservoir begins much farther away. Even the lower estimates for the inner cloud place it at distances vastly greater than the heliopause crossing. Voyager remains far short of that region. The cloud, if it exists as described, would therefore occupy a frontier beyond the reach of any spacecraft that has directly sampled the outer solar system. Its possible presence is known through objects that occasionally come toward us. A long-period comet becomes a messenger from a region that cannot yet be inspected directly. That contrast changes how the outer frontier should be imagined. A comet may spend most of its existence at a distance no spacecraft has approached, yet still follow an orbit shaped by the same Sun that governs Earth. Its return does not reveal the entire distant population. It provides one narrow piece of evidence, which becomes more meaningful when compared with other comet paths and with models of the gravitational forces acting across the outer solar system. Its orbit does not provide a complete map. It cannot reveal the total number of distant bodies, their exact distribution, or the full extent of the proposed cloud. But many such orbits, examined together, support the idea that a distant population exists. Questions remain. Scientists do not know precisely how many objects belong to the cloud. Its total mass is uncertain. Its inner and outer boundaries cannot be drawn with confidence. The shape may be more complicated than the simple spherical picture used to introduce the idea. And the influence of passing stars and the galaxy means the outer population may change over time. The correct description must preserve those uncertainties. The Oort Cloud is not a directly observed wall at the edge of the solar system. It is a proposed distant reservoir supported by the behavior of long-period comets and by models of how icy bodies could have been scattered and reshaped. If that interpretation is correct, the solar system extends far beyond the region where spacecraft first entered interstellar space. This creates a striking contrast. The heliopause can be measured through changes in particles and plasma. The Oort Cloud is inferred from the paths of returning comets. Both describe meaningful relationships between the Sun and its surroundings. But they do not occupy the same distance, and they do not define the same kind of boundary. One concerns the reach of the solar wind. The other concerns distant objects that may remain held by the Sun's gravity. If both are relevant, then the question that opened this journey becomes more difficult to answer with a single line. Where, exactly, does the solar system end? Where the solar system ends depends on what we believe the solar system includes. At first, That may sound like a way to avoid answering the question. It is the answer. The problem is that several different physical relationships connect the Sun to the space around it, and those relationships do not end at the same distance. Planets occupy one region. The solar wind fills another. Distant icy bodies may orbit through an even larger territory. Gravity extends farther still, gradually competing with the influence of the surrounding galaxy. Each relationship produces a different boundary. None can serve as the single edge for every meaning of the solar system. The first boundary is the simplest to recognize. If the question concerns the officially recognized planets, the planetary sequence ends at Neptune. Neptune orbits the Sun at roughly 30 astronomical units. Under the current definition, it is the outermost confirmed planet. That makes it the correct answer to the question of which known planet lies farthest from the Sun. But it does not make Neptune the end of the solar system. Beyond its orbit lie Pluto and other dwarf planets, smaller icy bodies, and objects whose paths extend through the outer frontier. The planetary boundary identifies the end of one category. It does not describe the end of all solar structure. The next useful boundary concerns the main region of the Kuiper Belt. Many distant icy objects occupy a broad population extending outward to roughly 50 astronomical units. Their presence shows that substantial solar system material continues beyond the final recognized planet. But 50 astronomical units is not a universal dividing line. The main population becomes less concentrated, while scattered and detached objects can follow orbits extending much farther. The belt does not end in a visible wall. Its outer region merges into a more complex distribution of bodies whose paths cannot be contained within one simple ring. This produces a dynamical picture of the solar system, defined by objects moving under the Sun's gravity and by the orbital relationships that connect those objects to the planetary system. That picture already extends beyond the limits of the familiar planetary diagram. Yet it still does not capture another boundary measured directly by spacecraft. The solar wind creates its own environment. Particles released by the Sun move outward until they encounter the surrounding interstellar medium. The region dominated by that outward flow is the heliosphere. Its outer boundary is the heliopause. For the two Voyager spacecraft, this transition occurred at distances close to 120 astronomical units, although the exact crossing distances differed. The measurements revealed a change in particle populations and plasma conditions. That makes the heliopause a real physical boundary. It is not merely a naming convention or a line placed on a map for convenience. A spacecraft moving through it enters a region where interstellar material dominates over the solar wind. If the solar system is defined by the reach of the Sun's outward particle flow, the heliopause marks its edge. Under that definition, Voyager entered interstellar space. But another definition produces a different answer. The Sun's gravity does not stop where the solar wind loses dominance. Objects can continue orbiting the Sun beyond the heliopause, even while moving through an environment associated with the space between stars. The proposed Oort Cloud illustrates that distinction. If the distant reservoir inferred from long-period comets exists as described, its inner regions may begin thousands of astronomical units from the Sun. Its outer extent could reach tens of thousands of astronomical units, perhaps farther. Those figures remain uncertain because the cloud has not been directly mapped. But the underlying possibility changes the scale of the question. A spacecraft could leave the heliosphere and still remain far inside a much larger population of bodies associated with the Sun. The surrounding particles might be interstellar. The distant objects might still belong to the solar system through gravity. These statements do not conflict. They describe different physical relationships. The same location can lie outside the Sun's particle-dominated bubble while remaining inside the region where objects continue orbiting the Sun. That is why Voyager's crossing cannot be treated as the final answer to every question about the solar system's size. It answers one question extremely well. Where does the solar wind stop dominating the surrounding environment? It does not answer the separate question of how far the Sun's gravitational family extends. Even the gravitational boundary is not a perfectly fixed shell. The Sun exists inside the galaxy, and its influence competes with wider gravitational forces. At very large distances, the galaxy and passing stars can affect whether an object remains associated with the Sun. The outermost relationship becomes less like a line and more like a region of competing influence. Some objects can remain loosely bound. Others can be disturbed, redirected, or eventually separated from the Sun's control. The exact limit depends on circumstances rather than on a permanent marker floating in space. This is the central realization. The solar system does not have one edge because it is not defined by only one kind of connection. The planets define a planetary frontier. The Kuiper Belt and other distant objects define an orbital and dynamical frontier. The heliopause defines a particle and magnetic frontier. The proposed Oort Cloud and the Sun's wider gravitational reach define a much larger, less certain frontier. These are not rival measurements of the same wall. They are answers to different questions. The distinction also explains why different scientists can describe different outer limits without contradicting one another. Each limit becomes meaningful only when the physical process being measured is identified clearly first. What happens beyond the last planet we know can now be stated directly. Beyond Neptune lies a broad region of icy bodies, including Pluto and other distant objects. Farther outward, scattered and detached populations extend the orbital structure beyond the main Kuiper Belt. The Sun's solar wind continues until it meets the surrounding interstellar medium at the heliopause. Beyond that boundary, the spacecraft-accessible environment becomes interstellar, while the Sun's gravitational influence continues. Much farther away, a hypothesized reservoir of comets may preserve the outermost material family associated with our star. Some parts of this sequence are observed directly. The planets and many distant icy bodies have been detected with telescopes. Pluto and Arrokoth have been examined closely by a spacecraft. The heliopause has been sampled through direct particle and plasma measurements. Other parts remain inferred. The Oort Cloud is supported by comet behavior and gravitational models, but its precise structure and extent remain uncertain. The possibility of an additional distant planet is still unconfirmed. Those distinctions prevent the answer from becoming more certain than the evidence allows. They also reveal why a single diagram can be misleading. A map showing only the planets omits the outer populations. A map ending at the heliopause omits the possibility of distant bodies still bound to the Sun. A map drawing a precise outer line around the Oort Cloud assigns certainty to a region that has never been observed directly. The more accurate picture is layered. Each layer marks a different relationship between the Sun and the space around it. Some relationships can be measured directly. Others must be reconstructed from their effects. Together, they replace the idea of a sudden ending with a frontier that changes according to what is being measured. The final planet is not a gate beyond which the solar system disappears. It is the last familiar marker before the Sun's neighborhood becomes harder to see, more difficult to define, and far larger than the planetary sequence suggests. What remains is not another scientific boundary to discover within this explanation. It is the question of how this wider understanding changes the way we imagine the place we call home. The darkness beyond Neptune looks different once its hidden structure becomes clear. At the beginning of this journey, it seemed natural to imagine the last planet as the final marker of the solar system. The familiar worlds appeared to form a sequence, and the end of that sequence seemed to leave nothing meaningful beyond it. But the outer solar system does not disappear when the planets stop. It becomes harder to recognize. Its remaining structures are spread across greater distances, revealed through weaker signals, and defined by relationships that cannot always be seen directly. Some connections appear in the orbits of distant icy bodies. Others appear in the particles flowing outward from the Sun. Still others emerge from comets returning from regions no spacecraft has reached. These are different ways of belonging to the same cosmic neighborhood. They do not all fade at the same place. A world can remain connected to the Sun through gravity long after the surrounding particle environment has become interstellar. A boundary can be physically measurable without representing the end of every object associated with our star. The solar system is therefore not a sealed container. It is an extended set of relationships. That understanding leaves important questions unanswered. Astronomers still do not know whether the unusual paths of some distant bodies point toward an undiscovered planet, or whether other explanations will prove stronger. The possibility remains open, but it is not a confirmed addition to the planetary family. The outer distribution of icy objects also remains incomplete. Some observations suggest that material may extend beyond the simplest description of the familiar distant belt, but the full arrangement has not been mapped. The heliosphere presents its own uncertainties. Spacecraft have crossed its outer boundary, yet their narrow paths cannot reveal its entire shape or show exactly how every part changes over time. The proposed Oort Cloud is more distant still. Its existence is inferred from comet behavior rather than established through direct images, and its size, shape, and population remain uncertain. These gaps are not signs that the investigation has failed. They show where observation becomes difficult. A telescope can detect only objects bright enough and favorably placed for observation. A spacecraft can measure only the environment along its path. A returning comet can reveal something about its distant origin without exposing the entire region it came from. Every method has limits. Each also provides a different opportunity. Future surveys may discover additional distant bodies and clarify whether unusual orbital patterns reflect a real physical influence or the incompleteness of present observations. Improved observations may help determine whether the outer population extends farther than familiar maps suggest. A dedicated interstellar probe, if developed and launched, could examine the outer heliosphere and nearby interstellar environment with instruments chosen specifically for those questions. These possibilities are not guarantees. They describe how the map could become more detailed as new evidence appears. What matters is that the basic lesson does not depend on resolving every uncertainty. The solar system already extends beyond the final recognized planet in several scientifically meaningful ways. Its material population continues. Its outward particle environment reaches farther. Its gravitational connections may extend across a territory much larger than the region any spacecraft has explored. This perspective changes the meaning of the darkness. The change is not merely a matter of adding more objects to a familiar diagram. It requires accepting that the sun's surroundings cannot be described by one shape or distance. A boundary drawn from orbiting bodies answers one question. A boundary drawn from flowing particles answers another. Neither cancels the other. Together, they reveal a neighborhood that overlaps with the wider galaxy rather than ending neatly before the galaxy begins. What once seemed like an outer edge becomes a gradual transition whose meaning changes with the evidence used to describe it. Darkness does not indicate absence. It often indicates that the relevant structures cannot be understood through visible landmarks alone. An orbit may reveal a body too faint to appear clearly. A particle measurement may identify a boundary no camera can photograph. A comet's return may suggest a distant reservoir that remains beyond direct observation. The outer frontier becomes known through traces. Each trace connects something remote to the sun and, indirectly, to the small world from which the investigation began. Earth occupies only a tiny part of this larger arrangement. Yet the same star that lights our days also shapes distant environments and holds faraway objects within its gravitational reach. That connection does not require a perfectly drawn edge. It emerges from the continuity between nearby planets and regions that can be understood only through careful observation and scientific inference. Return, then, to the imagined spacecraft moving beyond Neptune. The planet slowly recedes behind it. The sun appears smaller and more distant. Ahead, there is no signpost announcing the final limit of the solar system. No wall rises out of the darkness. No single line separates everything belonging to the sun from everything belonging to the galaxy. Instead, the spacecraft enters a landscape of fading influence. Distant bodies move through paths shaped by solar gravity. Particles from the sun give way to material from the surrounding interstellar environment. Farther out, unseen populations may preserve the history of a system whose outer limits remain difficult to define. The view still appears dark, but it no longer represents emptiness. It represents a region where familiar categories become less useful and where the boundaries of home depend on which connection we are measuring. The last planet is not the final page of the solar system. It is the point where the obvious landmarks end and the more subtle relationships begin. Some can be observed directly. Others remain uncertain. All of them remind us that a star's neighborhood is larger and more complex than the simple arrangement of planets once printed in a classroom diagram. Beyond Neptune, the solar system does not suddenly vanish. It gradually becomes harder to separate from the galaxy around it.